Okay.
So let me go back to the case study that I wanted to introduce to you. And I just would like to remind you that it refers to a reclamation consortium of this region, which takes water from a river and uses the water to irrigate fields. And this case study is particularly interesting because, as I mentioned to you, this is the consortium that provides irrigation to the area where the Parmesan cheese is produced. And the problem is a bit complicated because they experience a water shortage in this area. And it's a long story. It's not just today that they are experiencing the water shortage. They already realized about 150 years ago that there was a problem of water shortage during summer. And the idea at that time was to build a water reservoir, an artificial reservoir along this river, from which they take the water. The idea is, of course, that of storing water when there is plenty of water, typically during winter, spring, and autumn. They have a lot of water in these rivers, because in our climate, these kind of rivers that flows from the Apennines, they take a lot of rain during the cold season, and therefore the idea is to store the water that is available in excess during the season when we have plenty of water, to use the water for irrigation during summer. And this is a usual strategy in water resources management. When you have enough water, but water availability is not in phase with water demand. In phase, I mean in time phase, is not the water demand, the times in which you have water demand and the times in which you have the water available don't match. The usual strategy is to build a water reservoir if it's possible. In this case, you can compensate with this solution water availability along the year. This is a very classical solution. By the way, this is a solution that today is questioned and questioned because it has a great impact on the environment. In the past, people didn't care much on the impact of artificial reservoirs. Now, of course, we are caring of it because we realize that the impact is enormous. Okay, so basically this is the solution that they identified already 150 years ago, but the reservoir was never built for many reasons. In some period they had economical problems, they couldn't find the money to build the reservoirs. In other periods they were having problems because of conflicting views among the stakeholders. So, of course, there are people that take some advantage from a reservoir, typically the farmers, but there are also people who don't like this type of solution, typically the people that live downstream, if they are concerned by the risk of a flood, if the reservoir breaks. But also people living upstream, they typically don't take any advantage from a reservoir that is located downstream, because they can't take the water that is located downstream. They don't take any advantage from it. So typically, in some periods, they had some conflicts among stakeholders. In other periods, as I said, problems that were given by wars or economical problems. So they never realized it. They got very close to building the reservoir in 1980. The design project was completed and they started the works, but at the end they couldn't continue the works because the Green Party opposed to the construction of the dam. So basically this is a problem that still hasn't a solution, has not. And therefore there is still a lot of controversy related to this river, which is called ENZA, E-N-Z-A, and controversy related to the irrigation for the fields for the area where the Parmesan cheese is produced. You may ask me, what is the relation between irrigation and the Parmesan? The relation is given by the cows. The cows produce the milk, but they need to eat grass, and therefore in this area typically the main production, agricultural production, is grass for feeding the cows who produce the milk that we use to make the parmesan. Okay, the problem is that up to the recent past, people involved in this controversy, they realized that they didn't have enough water, but it was not clear how much the deficit was. And therefore, my task, our task at the department, was to estimate this water deficit. And in order to do so, I want to introduce the mathematical model that was used, that is based on a very simple water balance. You already know what is a water balance, and the model is based on a very simple application of the water balance. And let me explain how the model works. And before introducing the model, let me introduce the real system. When you build a mathematical model, you have to know very well the real system that you want to emulate. And what is the purpose of building a mathematical model? To reconstruct the numbers that you don't have. So, if you want to estimate water availability, in order to estimate the water deficit, why do you need a mathematical model? If you had the numbers, meaning the observations of water availability for a lot of years, you could just compare water availability with water demands. And then you get an estimate of the difference among the two. But if you don't have these numbers, a possible solution is to build a mathematical model. The mathematical model has the advantage that you can run it and get the numbers you're interested in. So if I don't know the river flow, if I were able to build a mathematical model simulating the process of river flow formation, then by running the model I get an estimate of the river flow in whatever period of the year, in whatever location along the river. So this is the purpose of building a mathematical model. To emulate a system, a real system in our case an environmental system. We want to emulate it because we want to reconstruct some variables which we need and for which we don't have any observation. It's clear that in this modus operandi there is uncertainty. It's clear. It would be better to observe the system and use numbers that I really saw, numbers that I really measured. Of course, we know that a mathematical model cannot replace the observation of nature, of environment. There is uncertainty in it. But still, if we don't have the observations, even that we can't go back in time and take the observation that we need, we have two solutions. Either we say to our customer, to our clients, please install a monitoring station and come back in 10 years and I will give you the numbers, or we build a mathematical model. And of course, if you want to build a mathematical model, we will learn how to build a mathematical model of hydrological systems. But of course, the first thing that I recommend to you is to gain a knowledge, a personal knowledge of the system that you want to emulate. Because if you don't know the numbers, at least you can know the principles. You can understand the system, because you need to provide an interpretation, and the interpretation should be based on information, understanding. Okay. So let me explain how the system works. There is a river flowing, and at a certain point along the river there is a barrage. A barrage from which part of the water flowing into the river is diverted to a canal. And you saw some pictures the other day that I showed you. You may remember that there was a canal whose water was divided 50-50 with a particular hydraulic work. This is the canal. So there is a barrage in the river, the water is diverted from the canal, and the canal brings the water downstream with a long travel, of the order of magnitude of from 15 to 40 kilometers. Not really long, but it becomes quite long because it's not just a unique canal, it's a big one that then, from the big one, small canals are take place, and then from the small canals, even small ones, and so the network is really very articulated, well articulated. So it's a quite long trip, and these canals typically, they are not made by, I mean, the riverbed and the levees are not made by concrete. They are just canals that are digged into the soil, and therefore they are like natural canals, let's say. So there is infiltration. The moral of the story is that you have some water losses, because of course if you pave the riverbed and the levees, then you minimize infiltration and water losses. But if you don't pave the canal, you have water losses. On the other hand, if you pave the canal, people would complain because the paving has an environmental impact. So basically the water flows into the canals, and then the water is used for irrigation. And in order to be able to provide water to all farmers, they apply a rotation procedure, a rotation policy. And this is quite easy to conceive. They have a long historical experience on that. And if you have enough water, rotation is fine. The problem is then the type of irrigation technique that they use. Because there are several types of irrigation techniques, and now we know that if you want to minimize the water losses, sprinkler irrigation, namely rain irrigation, artificial rain, is the most advisable. So you use the water and you push the water with high pressure into a sprinkler that creates artificial rainfall. This is one possible type of irrigation. The problem is that it's energy demanding because you need to put the water under pressure. So you need a pump. Even if you have the water available at the level of the field, you need a pump because you need to put the water in pressure, under pressure, in order to make the sprinkler working. Another possibility is what is called flood irrigation, which in Italian is called irrigazione per scorrimento, just to be clear for those of you that are from Italy. And flood irrigation means that you have the water available at the level of the field, and from the canal you just let the water flowing over the field. And the field should be a bit tilted, I don't know how to pronounce it, means inclined, so that the water can flow over the ground. And this is a type of irrigation that is historically applied in this area. And the reason is that in the far past, they didn't have pumps available, so they were forced to use flood irrigation. So still they are using flood irrigation, but you can easily understand that flood irrigation is consuming in terms of water resources, because you have a lot of water losses. At least because you need to generate an excess of water to be sure that water reaches the end of the field. So if you want to really make sure that you get flood irrigation, means that you let the water flowing over the field, so you have at the beginning some infiltration, and the water doesn't get much far from the canal, but then the ground saturates and then the water gets much farther. And if you want to make sure that you reach the end of the field, the point that is located more far from the canal, you have of course to give an excess of water to the field. And this water cannot be recovered. So basically, flood irrigation is still used, and therefore possible. Okay, I understand, but there is the other door. Okay, there was another door here, so this is the reason why I didn't understand. And as I said, a possible solution is, of course, to replace flood irrigation with sprinkler irrigation. But there are two buts. First, energy consumption. Second, which is more important, is that people are skeptical, because when you have a historical tradition of people working in one specified way for centuries, then when you get to people and say, okay, look, from today we change, you get problems. Remember, change is always tough for everything. Change can be stimulating, it can be really exciting, but at the end is always tough. When you have people that are used to work in a certain manner, or people that are used to live in a certain manner, when you go to these people and propose them to change, it's always a problem. So basically they don't want to change it. And why? Because they are concerned by the fact that the quality of the Parmesan cheese could be affected. Because indeed the Parmesan cheese, like many other typical products, it's a mystery. You know that the Parmesan cheese can be produced only in that area. If you try to produce the Parmesan cheese somewhere else, you don't get the same cheese. So it's still a mystery why you get this particular flavor of the Parmesan cheese only there. So people, given that they know that it's a mystery, of course, when you propose to change something, whatever, even irrigation, they get concerned. They say, okay, but then the quality of the Parmesan. So basically, in this area, they made an experiment. And this is an interesting thing that I'm pleased to report to you. They decided to make an experiment to convince the farmers to use sprinkler irrigation. They took 2 farms and made a contract with the farmers and paid for the sprinkler irrigation for a couple of years. And then they measured, first of all, the amount of water that was used for irrigation and the amount of grass that was produced. And there was a saving of the water of 40%, which means that with more or less half the water they could irrigate, getting the same production in terms of grass. And then they fed the cows with the grass and produced Parmesan just by using only the milk from that cows. And then they organized a taste competition. They called people expert in Parmesan tasting, because we have some international experts in Parmesan tasting, and they were given the 2 types of Parmesan to taste, and they couldn't find any difference. Still, people don't want to use sprinkler irrigation. So you understand the complexity of the water resources management problem. Okay, having given to you the basic concepts of the problem, I'm speaking quite quickly because this is just a case study, and I see some of you taking notes, but of course I'm not asking anything at my exam about this case study. But still, if you want me to repeat or to speak slower, just let me know. So let me introduce the mathematical model. This is interesting. First of all, we start from the upper left panel, where you can find written water demand at the field. This is the first challenge. How much water do I need to irrigate a field of grass? So it was computed, the amount of water that we need at the field, by considering the spatial distribution of the crops. We don't have only this crop there. We have some reduced extensions, agricultural areas where they cultivate other crops. So it was made an inspection and assessment of the spatial distribution of the crops, and then we went to the literature to see how much water is needed for each crop. And then we took into account the climate, because even in a small region you have spatial variability of climate. Because if you go uphill, you get more rain. If you go downhill, you get less rain and higher temperatures. So we took into account the spatial variability of climate. We took into account the spatial variability of permeability. And because, you know, in a more permeable soil, you need more water. Because with flood irrigation, you need to get to saturation. And therefore, you need more water if the soil is permeable. And then we took into account also water availability, meaning that if a farmer is located close to the river, he tends to use more water. Instead, if a farmer is in a condition of water scarcity, he saves water. We took into account also this, and also the type of irrigation technique. And we were able to estimate the water demand at the field and we decided to make the model working at daily time scale. So for each day during summer, we estimated the water demand at the field. And also, there is to take into account that we decided to perform the simulation with respect to a recent period. We decided to simulate with the model the period between 1990 and 2000, so 10 years. 10 years at the daily time scale, only for summer, and therefore, by looking at the meteorological condition, we were also able to see when it rained and when it did not. So when we noticed that it was raining, we reduced the water demand at the field accordingly. So basically, once that you estimate the water demand that is in general needed for a region, you can adjust the water demand for a given historical period if you look at the meteorology of that period. And this is what we did. So for each day we went to see how much rain we got in that day, and then we corrected the water demand. Okay, at the end we were able to estimate for the period 1990-2000 for each day during summer how much water we needed. And then you have to convert this water demand at the field in water demand at the river. What's the difference? The difference is given by losses. So through an estimate of leakage in the canals, we were able to estimate the water demand at the river. And this was a long story because people provided different estimates for the leakage. And so we made an experiment. We went to a canal and we measured the water flowing, entering into the canal, and the water exiting downstream 50 kilometers. And we repeated the measurement for several days, and we were able to see that an average water loss in this consortium is 50%, which means that half of the water that you get from the river is lost from irrigation, from infiltration, from the canals to the ground, which is, you may say that it's unbelievable, it's too much, but indeed it's normal. If the canal is not paved with concrete, then the loss is more or less for a length of the network of this order of magnitude is about 50%. Keep in mind that in Italy, the water losses in the aqueducts, which, you know, the flow in the aqueducts is through pipes, but still you have leakages. The water losses in Italy are about 30–40% for aqueducts. So you shouldn't be amazed to see that for water distribution systems that use canals, the water losses are 50%. It's normal. But basically this means that you need to get twice the water at the river that you need at the field. Okay? And then, at the river level, we ran the water balance because from 1990 to 2000 we had observations of river flow. It was a lucky situation. Still, the observations were a bit questioned by people, but we had them. So for each day of the summers of these 10 years, we were able to compute the difference. Available minus demand. And if the difference is positive, you are happy. If it's negative, it means that you have a deficit for that day. Okay? And then we got the water deficit at the river. Then we went back to the field, because at the river, I'm working on twice water amounts with respect to the field. So if the deficit at the river is 10, at the field the deficit is 5. So through leakage, we went back to the field. And finally we got an estimate on the average annual deficit. These numbers don't tell you much, because you don't know the situation. You see two rivers here, because one is the river we are interested in, and the other one was a river that we selected for comparison. And you see that indeed, in a year, a deficit of about 50–60 million cubic meters of water is considerable, because It's the size of a medium-sized dam. And if you think to the size of the Bayonne dam, for instance, it was, I don't remember, I think it was 250 million cubic meters of water. So 60 millions, it's a reasonable amount of water at the field. And there is to say, the question now would be, what would be the size of the reservoir that they want to build there? The size would be 120 million of cubic meters. So it would be the correct size to compensate this deficit. Okay, this is the model that we built. And the model was very simple, because you see that it's just based on a difference between water availability and water demand. What was complicated is to put the people together and reach an agreement on the leakage, on the water demand, on the type of irrigation that they should use, etc. This was the problem. Now, of course, one solution is the reservoir, but we proposed other solutions because, you know, this reservoir has a problem that is very huge. And also, we are a bit concerned by the impact because you don't know the impact of a reservoir, the actual impact, until you build it. So you can make a guess of the impact that the reservoir has on the climate, on the groundwater flow, on the ecological system along the river. But in this case, there were some concerns related to the fact that the main concern, my main concern, was that the bed load of the river is very significant. And so I am a bit concerned that this reservoir in 50 years will be completely filled up by sediments. And if this happens, it means that you are wasting a natural resource, and for just 50 years of solution, it's not really very interesting. And keep in mind that removing sediments from reservoir is a huge problem for which still there are not very satisfying solutions. It's a very huge, very challenging problem because there are many questions. How do you dig? How do you remove these sediments? And this is relatively simple. One may say, okay, remove the sediments with excavators or other type of machines, but then where do you put the sediments? Because you can't release sediments downstream. It has an ecological impact that is tremendous. It's very bad thing for the ecosystem, the fishes, etc. So it's a relevant problem. So basically the solution that we suggested was to change the irrigation techniques and to build smaller reservoirs along the river floodplains, because they built, in the floodplains of this river, floodplains means it's Golene in Italian. In the floodplains, they used to dig lakes, small lakes, because they used to take the gravel to be used to make the concrete. And so there are still some holes in the floodplains, and if these small lakes are managed, then they could provide a solution. The problem is that the cost of building many small lakes is much significant, and in this period of economical problems, it's not so easy to convince the public administrator to adopt the solution. I'm not going into the details, and then here you see irrigation. Flood irrigation on the left, sprinkler irrigation on the right. And another interesting experience that has been done, not in this particular area, but in the Emilia-Romagna region, is the use of a web system for managing irrigation. And basically, the web system is used by farmers in order to decide how much water to give to the fields. And the web system is based on a spatially distributed knowledge of the lands, of the irrigated lands. So it's based on a database, and also is based on meteorological prediction, forecasting. So the web-based system looks at the meteo forecast, and then suggests the amount of water to be used to the farmers. And this is a successful story because indeed there were some concerns before related to the fact that some people thought that the farmer wouldn't be willing to use it. Indeed, this was not true, because the farmer at the end were willing to use this web system because they realized that they could save money. In general, when you deal with a stakeholder, you have to, in order to make him happy, you have to maximize his, of course, economical convenience. And I should have, okay, this is a rendering of the reservoir that I was talking about, which is, of course, was not big, as I told you, but still, some people claim that this would be the optimal solution. I don't think it's a solution that it will be adopted because it's too costly, even in this case, and therefore, I don't think we will end up building it. But there are similar reservoirs that were built recently in Italy, in other regions, so it wouldn't be really an unusual solution. There is one thing to say. I go back just 1 second. If you look at this reservoir here, during summer, the surface of the lake, you see the lake in condition of full storage. During summer, of course, the lake would minimize its storage because this is a lake that is used, water that is used for irrigation. And given the morphology of the region, reducing the storage of the lake would imply that the surface of the lake would decrease 80%. Can you imagine how this picture would become during summer? Just a brown spot with just a small lake in the center. So this is something that is also concerning for the look of these lands. They are very nice lands, and during summer they will become just a mud area where people cannot walk in because of the water. Otherwise, of course, it's dangerous. It becomes dangerous. So there are several environmental concerns. Okay, I think I can move to the next step. I would like to try to adjust the resolution of my screen. It's really challenging. Okay, now I am using, let me see if I can see. I am using one of the files that I made available on my website for the next story. And I updated the file today, just in a few slides. So if you already downloaded it, I suggest you to download it again, because today I made a few changes. It's not really, they are not really relevant changes, but let's say that it's better if you download it again. And I am now downloading myself the updated one because I don't have it here on this PC. Here it is. Just 1 second, I complete the download really quick. The topic that I am introducing now is rainfall runoff modeling, and it's related to estimation of water resources availability. Rainfall runoff modeling basically uses a mathematical model to reconstruct the river flows. And as I mentioned to you before, we can use mathematical models to get the data we are interested in when observations are not available. In this case, I am assuming that the need is to estimate water resources availability from a river. And in absence of observations, there are several solutions that can be applied to simulate the observations. So basically, if the observations are not available, we need to simulate them, and there are several solutions that can be applied. One possible solution is to use rainfall runoff modeling. So starting from rainfall to generate runoff. And you may ask me, what is the reason why we use rainfall runoff modeling? Because you may say, if you don't have river flow data, you may not have rainfall data as well. But the advantage with the rainfall data is that they are more readily available. Because while measuring river flow is a problem, and I'm not teaching in this subject how to measure the river flows, but indeed, because I'm teaching this topic in hydraulic works, in my lecture on hydraulic works, it's a topic that is not directly related to water resources management, but I can tell you that it's very complicated to measure the river flow. And therefore, the measurement is done only in a few river gauging stations only. So basically, river flow measurement is very sparse. And as a consequence, it's very unlikely when you decide to take water from a river that you have measurement of river flow in that river. It's very unlikely if you decide to build an hydropower plant on a river that you have measurement of river flow for that river. And therefore you need to estimate river flows to assess water resources.